Every passenger jet is a traveling life support system, carrying inside it the highly pressurized oxygen that keeps us alive. If it ever escapes, a simple flight becomes a living nightmare. United 811.
There was nothing in front of us or to the side of us. The whole side of the plane was gone.
Aloha 243.
Everything was being sucked out of the plane.
British Airways 5390.
I'll never forget, his face was hitting the side screen, but he didn't blink.
Mayday, mayday, mayday!
Declaring an emergency!
Sometimes it takes a terrible accident to expose hidden dangers and change the way airplanes are built.
Unfortunately, we wait until we have enough bodies. Too many of the changes have been, in effect, written in blood.
Mayday, mayday!
This is the assembly plant for the Airbus A320. After the Boeing 737, it's the most popular jet plane ever built. Almost 2,000 of them are flying for airlines around the globe. It's safe and dependable, the airline equivalent of a minivan. The aluminium skin on the top of an A320 is less than 2 millimeters thick, about as thick as a coin. But this slender piece of metal helps keep passengers alive. Because the skies aren't nearly as friendly as they seem.
Most people take aviation absolutely for granted. The difference between being in a commercial airliner at 35,000 feet and being in a space capsule in orbit is really not all that different. They're both life support systems. The reality is it's a hostile environment. The reality is it's 50 degrees below zero outside. The reality is that jet stream or that airstream out there would kill you almost immediately.
It's not natural for people to travel through this killer atmosphere. But every day, millions of us fly easily some 3,000 meters higher than the top of Mount Everest.
All our life support that's natural for us is down here at the bottom of this sea of air. And if we swim up too high, however we get there, if we're not protected, we can't live.
But taking oxygen with us up to 11,000 meters is potentially dangerous. The air inside an airplane is pressurized, so passengers can breathe easily. As planes climb, the pressure outside decreases. The tightly packed air in the cabin begins exerting tremendous pressure on the fuselage. On an average jetliner, it means that every square meter of the fuselage must support more than 5,000 kilograms of force. And on almost every flight, the fuselage wins the battle. But only because airplane designers have learned tragic lessons.
We have concentrated in the past on changing things, but unfortunately we wait until we have enough bodies.
In the 1950s, a series of shocking accidents triggered changes that are still seen today.
The comet has blazed new trails, achieving new speeds, setting a new standard.
The passenger jet era began in the 1950s with the introduction of the de Havilland Comet. For the first time, jet engines were being used to push commercial planes higher than ever before.
What Great Britain had at stake with the Comet was enormous. They wanted to really declare their place in civil aviation by having the first successful jet transport aircraft.
But less than 2 years after its maiden flight, the glittering jewel of British aviation disintegrated in mid-air.
It would have been horrible. It would have been a horrible situation, but mercifully it would have been quick. What they had found with the bodies that they had recovered is the massive decompression, of course, caused the air inside your lungs to burst your lungs. At the same time, the outrush of air would tear you from your seat, and many of these people would actually smash their heads against the structure.
3 months later, another comet ripped apart in flight. Officials feared that every single comet could be a flying time bomb. The entire fleet is grounded.
The design of the comet was actually a very sound design. There was only one thing that they didn't do, and it's because nobody knew.
Unknown to engineers, there was a deadly flaw in the comet's basic design. To find the jet's fatal weakness, investigators built a massive water tank. They immersed a stripped-down comet. The pressure in the tank was increased and decreased, simulating the strains of flight. The experiment ran 24 hours a day, 7 days a week. After the equivalent of some 3,000 flights, the comet's Achilles heel revealed itself. Its square windows.
You have a rapid change of direction in the shape, essentially a corner. You have a high stress concentration. It gave rise to a fatigue crack, which then traveled rapidly through the rest of the structure, causing a massive decompression.
The most advanced passenger jet in the world had succumbed to metal fatigue. The fuselage simply could not handle the force of the air inside, pressing out.
The airplane, with all that force behind it, suddenly unzipped itself.
Every plane that's built today is safer because of the disaster that struck the comet. Like other passenger planes, the windows on the A320 are rounded so that pressure doesn't build up around the corners. Perhaps even more importantly, extra rivets reinforce the skin of today's planes to contain cracks that might start anywhere on the fuselage.
It's designed to go to that first row of rivets and absolutely be stopped. It's a healthy structure. It can never unzip itself.
But 34 years after the comet crash, aircraft manufacturers were faced with another tragic disaster. The extra rivets that were supposed to save lives failed to withstand the relentless power of air pressure on metal.
One of the fellows that I knew at the FAA, he said, you know, the day after this accident, I had to throw away most of what I knew about metallurgy and start over.
At this Airbus factory in Toulouse, France, A320s roll out at about the rate of one every working day. Titanium rivets, lightweight and extremely tough, hold the fuselage together. 3,000 are used to join the separate sections. Another 3,000 can be found on each wing. Without them, the fuselage couldn't contain the pressurized air that's forced inside during flight. But even these rivets aren't foolproof. April the 28th, 1988. Aloha Airlines Flight 243 is traveling from Hilo Airport on the Big Island to Honolulu. With this island hop, Aloha 243 is making its 9th flight of the day, a normal schedule for the planes of Aloha. Protected within the jet, passengers give little thought to the fact that the cabin is filled with pressurized oxygen. It's constantly pushing against the fuselage, trying to escape into the surrounding atmosphere. In the cabin, the pressure is kept at a constant level, so passengers feel like they've never left the ground. But as a plane rises to its cruising altitude, the air pressure outside the cabin is dangerously low. The air moving through the cabin creates constant pressure on the jet's fuselage, keeping it inflated like a balloon. On this day in April 1988, passengers are about to learn what happens when that air suddenly escapes.
I saw a brilliant flash of light and boom.
Everything was being sucked out of the plane.
Aloha Airlines 243 has just suffered what experts call an explosive decompression. The air inside the plane that makes jet flight possible escapes in a sudden horrifying moment. 35 square meters of the fuselage are gone.
Just imagine the scene up there. The top of the airplane broken off. You now have 300-mile-an-hour winds blowing into that cabin. That's 3 times hurricane-force winds. Those people were dressed for Hawaii in the springtime, not minus 50-degree temperatures. Any period of time at 24,000 feet, and those people will die.
What was that? We have to get down!
Captain Bob Schornsteimer begins an emergency descent, dropping 20 meters a second. The stress on the damaged craft threatens to tear it apart.
Woman that was sitting next to me and her husband, he was on the other side in the next row up. She was next to me and they were reaching their hands out and they were trying to touch fingers to say goodbye.
Against incredible odds, the flight crew land their bruised and battered airplane. Even with this explosive decompression, there's only one death on Aloha Flight 243. A flight attendant who was pulled out of the plane. Jim Wildy investigates the crash for the National Transportation Safety Board. In his laboratory, Wildy makes a disturbing discovery. Running through some of the pieces of the plane's fuselage, he finds a series of hairline cracks. They're right beside the holes created by rivets and barely visible to the naked eye. But they're classic signs of metal fatigue. A plane isn't a rock-solid tube. To maintain the pressure passengers need to enjoy a flight, it's designed to be much more flexible.
The fuselage of the airplane is actually breathing. It expands and contracts depending on altitude. When it's on the ground, it's in a contracted status. When it's at altitude, 24,000 feet, the fuselage expands. So the airplane is constantly cycling. That's pressurization. That will weaken the structure over a long period of time.
Records show that the Aloha jet was 19 years old. 737s are designed for a 20-year service life and a recommended 75,000 flights. But as investigators take a closer look, they discover that the Aloha jet had logged an astonishing 89,000 separate flights. The short hops between the Hawaiian Islands meant that the planes in the Aloha fleet went through more pressurization cycles than any other aircraft.
You saw something as you got on this airplane. What did you see?
Investigator Jim Wildy gets a lead when he interviews one of the Aloha passengers. She says she saw a small crack in the fuselage just to the right of the door.
The witness saw cracking in this area, and we found fatigue cracking back in here. So this is the line where the fatigue cracking joined up. One piece came down this way and folded off, and the other piece went across the top and came off to the right side.
But something doesn't make sense. The Aloha jet lost 35 square meters of its fuselage. In the years after the Comet disaster, Boeing and other companies had designed a safety feature that should have kept any tearing to an absolute minimum. Inside the fuselage of every 737, Boeing has installed a series of tear straps. If any kind of tear develops in the fuselage, it should only run as far as the next tear strap, never more than 13 centimeters away, before shooting off at a 90-degree angle. This would have prevented the sort of catastrophic disintegration that ripped apart the Comet.
The purpose of the tear strip is to confine any kind of rip or tear in the fuselage skin to a 10-inch square, basically. The 10-inch square allows a controlled decompression and confines any structural damage to a very small area.
But for Aloha 243, the tear straps did not contain the rupture caused by the metal fatigue. The NTSB believes there were so many cracks in the fuselage that they eventually joined together, tearing an enormous hole in the plane. But jets aren't held together by rivets alone. The Comet disaster had also highlighted the need to reinforce the fuselage. The skin of an airplane is built from separate panels which overlap. These panels are bonded together by a powerful adhesive known as epoxy. As the epoxy hardens, the panels are locked together by rivets. And during his investigation on the Aloha fuselage, Jim Wildey finds discoloration inside some of the overlapping joints.
You can see now where the dark material is the epoxy that was used to bond the two layers of the lap joint together. The white material you see here is corrosion damage of the aluminum fuselage skin.
The Hawaiian climate is great for tourists, but it's tough on airplanes. The ocean air is humid and heavy with salt. It can corrode even industrial epoxy. Investigators learned that Boeing, the company that built Aloha 243, had issued numerous written warnings about the epoxy. If it isn't applied at the right temperature, if the panels have moisture or dirt on them, the bonding can fail. Boeing recommended regular, detailed inspections. But workers at Aloha didn't report any problems with the epoxy. They either never saw the compromised epoxy, or if they did, it wasn't repaired. The Aloha accident was another step towards making passenger jets safer.
It's important to always learn from your mistakes. It's important to learn lessons from that. And that has been the case with aeronautical engineering.
The Aloha story was a brutal lesson in the dangers of metal fatigue. But it wasn't the last example of the power of cabin pressure. Two years later, the industry would get another terrifying reminder.
Ladies and gentlemen, this is your captain speaking.
My name is Tim Lancaster. Welcome aboard this
British Airways flight to Malaga.
June the 10th, 1990. British Airways Flight 5390 is leaving Birmingham, England for Spain. 87 people are on board.
80 knots.
Two minutes into the climb, the flight crew switch on the autopilot. Captain Tim Lancaster takes off his shoulder straps.
Now I went into the flight deck to ask Tim and Alistair what they would like to drink.
You gentlemen like a tea? Please, the usual.
Minutes later, at 5,200 meters, the plane is very close to its assigned altitude. And then, like a cork out of a champagne bottle, the windshield bursts from its frame. Captain Tim Lancaster is sucked out of his seat and is pinned to the fuselage by blistering winds roaring close to 550 kilometers an hour. The temperature is minus 17 degrees centigrade and there's very little oxygen. Co-pilot Alistair Atchison is alone at the controls. Ordinarily, cockpit windows cannot budge from their frames. The force of the air as the plane soars through the sky pushes the windshield onto the plane. But on Flight 5390, something has gone terribly wrong. Flight attendant Nigel Ogden rushes in to help.
And I looked in, the flight deck door was resting on the controls, and all I could see was Tim out the window. I just grabbed him before he went out completely.
Other flight attendants do what they can. Co-pilot Alistair Atchison reduces speed and descends quickly. But as he slows the plane down, the drop in wind pressure lets the captain slide around on the side of the plane.
All I remember is Tim's arms flailing out. His arms seemed about 6 foot long. And I'll never forget that. His eyes were wide open. I mean, his face was hitting the side of the side screen. But he didn't blink. And I thought to myself, and I said to John, I said, I think he's dead. I think he's dead.
Just 35 minutes after taking off, Acheson gets his jet safely back on the ground. But the most unbelievable chapter of this entire story is the fact that Captain Tim Lancaster survives his incredible ordeal.
But I remember watching the windscreen move away from the aircraft, and then it had gone like a bullet. It disappeared into the distance. And I was very conscious of going upwards. And, well, the whole thing became completely surreal then, as it would. And I was aware of being outside of the airplane. I can remember seeing the tail of the aircraft. I can remember the engines going round. And then I don't remember much more.
Tim Lancaster was pinned to the outside of the plane for over 20 minutes. His injuries were surprisingly minor. Bone fractures in his right arm and wrist, frostbite and shock. Within 5 months, Tim Lancaster was flying again. In the immediate aftermath, investigators have very little to go on.
Windscreen was missing, there was a certain amount of blood around, there were some minor dents and scrapes on the fuselage, as you'd expect if the window had gone past, and really that was about it, apart from a lot of paper scattered around inside.
The maintenance log is recovered from the plane. Stuart Culling learns the windscreen had been replaced just hours before takeoff.
Everything okay? Fine. Should just come out of maintenance by the look of it. Nothing much though. Just changed the windscreen.
I wanted to find out exactly what had happened to the aircraft before it took off.
Early in the investigation, the missing windscreen is found. It contains a curious piece of evidence.
There were something like 30 bolts found with it, most of which were one size short in diameter, one size too small in diameter.
On many planes, windscreens are fitted from inside the cockpit. Internal cabin pressure pushes against them, keeping them in place. But on the BAC 111, the windscreen is bolted from the outside. The pressurized oxygen inside the jet pushes out against the windscreen. The bolts must resist this pressure.
There are enough of them there that they simply can't pull out of the structure. But of course, if you then violate the very premise of that by putting the wrong bolts on, all bets are off. You're now a test pilot.
During his interview with the ground engineer who repaired the plane, Culling gets a major break.
One thing that came out was that he said, oh, the old bolts went into a waste bin in the hangar where he did the job, and they may still be there. So we rushed across to the waste bin and found something like 80 discarded bolts.
The old bolts are the proper size. Why were smaller bolts used to replace them?
And these are the ones you checked against the new ones?
That's right, yeah. I took
from the carousel.
There's really excellent evidence. Gold as far as I was concerned.
Instead of using the old bolts to put the new window on, the ground engineer decided to replace them. He did not check the parts catalogue to verify which bolt he needed for the job.
Morning.
The bolts he chose seemed the same, but in fact were just over 0.5 millimeter smaller. They were too thin to do the job. Early in the morning, working against the side of a hangar, the engineer couldn't tell the difference. Hours later, the window gave way. Faced with a challenge they weren't trained for, the crew still managed to pull their plane back from the brink. But the massive pressure inside an airplane doesn't need bad maintenance to rip a jet apart. That pressure can also find a tiny flaw somewhere in the design and cause a nightmare in the sky. The Airbus A320, one of the most popular passenger jets in the sky. Every day around the world, thousands of passengers board this plane. When they do, they walk through what would seem to be an obvious weak spot in the fuselage, the door. Any hole in the fuselage is a potential danger. So engineers designed passenger doors that can't be opened in flight.
It is virtually impossible, I don't use that word very easily, but it is impossible for a passenger to open a plug-type door in flight.
Passenger doors are plug-type doors. They're built to be slightly larger than their frames. When a plane takes off and pressurizes, the atmosphere inside the aircraft seals the door shut.
That door probably has 10,000 or more pounds of pressure holding it firmly in place in that door frame, and you have to pull it out of that door frame to get it open.
But not all doors on an airplane are built the same. Even designs that seem flawless on paper can rip apart in the real world. February the 24th, 1989, Honolulu Airport. United Airlines 811 is bound for Auckland, New Zealand. Expected flying time, 9.5 hours. There are 355 people on board, plus a full load of cargo. The doors close on time, and the plane leaves the gate just after 1:30 in the morning.
Tell them we can handle 33 if it's available.
Okay. We did notice that there were thunderstorms 100 miles south, right on course, which was rather unusual for that time of night, so I left the seatbelt sign on.
Captain Cronin's decision to keep that sign on will save lives. As the 747 climbs past 7,000 meters, passengers sitting just above and behind the cargo door begin to hear a strange noise.
Kind of a grinding noise.
I heard like a thud.
The hell?
In the next nanosecond, it was pure, unadulterated pandemonium.
The next thing I knew, I found myself on the stairwell, hanging onto the rungs, and I immediately knew it was an explosive decompression.
Everything on the airplane that wasn't fastened down, tied down, or secured became airborne. The noise was incredible.
The 747's cargo door had torn off, ripping away a section of the fuselage. The pressurized oxygen in the cabin shot out with explosive force.
And as I looked up, that was the first time I saw this tremendous hole on the side of the aircraft that was just a void, and seats were missing, and I immediately knew that we had lost passengers.
Everything in front of us was gone. Where we were sitting, we were about 6 inches from the hole, so there was nothing in front of us or to the side of us. The whole side of the plane was gone. Actually, our feet were dangling on the hole, and I first thought we weren't going to make it. You know, I just didn't think there was any hope.
The situation is desperate, but by itself, an explosive decompression won't bring a plane down.
In 811, there's a hole as big as Tulsa in the side of this thing. I mean, it's an aerodynamic disruption of massive proportions, but if it was designed the way we had designed things a long time ago, it would have unzipped.
After the door came off, eventually a row of rivets held, keeping the plane from pulling itself apart. But the gaping hole is putting massive stress on the aircraft. The flight crew needs to descend as fast as possible.
Left, right, valves on.
Start dumping the fuel.
I am dumping.
Struggling to fly their badly damaged jet, the crew turned back to Honolulu Airport.
And all of a sudden, we were slowing down, and I said, oh my God, we've landed, we're on ground.
Probably the best landing I've ever made. When we finally stopped on the runway, we deployed all 10 chutes, and the flight attendants evacuated all the passengers.
Thanks to the experienced flight crew, United Airlines 811 landed with everyone on board alive. But 9 passengers were missing, sucked out of the plane when the fuselage tore open, taking with it 5 rows of seats. One of those passengers was a New Zealander on his way home, Lee Campbell.
We got a phone call from Chicago, and they just said that they regret to inform us that our son was missing, presumed dead.
In the wake of their son's tragic death, Kevin and Susan Campbell embark on an international mission to discover exactly why the door had come off the plane.
Lee can't have died for nothing. You know, you've got to find out why he died, and you've just got to make sure that it never happens again.
2 months after the accident, the National Transportation Safety Board holds preliminary hearings. During a break, the Campbells take matters into their own hands. They remove several boxes full of files.
So we quickly realised we'd got a really good set of papers with a lot of things that hadn't been released to the public. We were able to really start our investigation in earnest at that stage.
The unpublished documents reveal a disturbing catalogue of problems with the 747's forward cargo door, going right back to its original design. Passenger doors are plug doors, but most cargo doors on jets open outward. This increases the space for luggage and other cargo. As the plane gains altitude, the pressure inside the jet presses outwards against the door. To prevent the door from opening, Boeing had installed what it believed was a foolproof locking system.
What they do is they build in multiple redundancies to make sure the door is properly latched and does not open. And you build it in to a point of that it's extremely improbable that the door would ever open.
The Campbells' research uncovers 2 major flaws with the 747 cargo doors. The first involved the locking system. To lock the cargo doors, electric motors turn C-shaped latches around pins in the doorframe. A handle then moves arms or locking sectors over the top of the C latches to prevent them from reopening. But on Flight 811, the supposedly foolproof system had failed. Kevin Campbell built a model of the 747 cargo door latch. It showed the first deadly flaw in the locking system. Aluminium locking sectors could not hold the C-latch in place if the latches started to open on their own.
With the aluminium locking sectors, if the C-locks tried to backwind, open electrically, it would just push the locking sector out of the way. It just simply wasn't up to the job that it was designed for.
But what would cause the C-lock to backwind? The Campbells didn't have the answer, but they knew they were onto something. During their research, they learned that 2 years before Flight 811, a Pan Am 747 out of Heathrow had pressurization problems as it climbed to cruising altitude. The pilot was forced to turn back.
When they got back to Heathrow, they found that the door was hanging open 1.5 inches at the bottom, and all of the locks were open. When it got to the maintenance base, they found that all of the locking sectors were either bent or broken.
The passengers on this flight were lucky. They had survived the faulty locking system. But why had the C-latches turned and bent the locking sectors? As the Campbells continue to search, a Pan Am report surfaces that lays out a critical issue with the cargo door's electrical system. When the cargo door's outer handle is placed in the closed position, a master lock switch should disconnect the power supply. This would stop the C-latches from turning. But something was wrong with the switch.
There was power to the door locks with the outer handle closed, and the lock started to move, and it started to force the locking sectors out of the way.
The faulty power switch and weak locking sectors were no match for the pressurized oxygen inside the plane. After years of being pushed by the Campbells, the NTSB produces a report that agrees.
There was an inadvertent failure of either the switch or the wiring that caused an uncommanded opening of the door.
It's nice that other people know that you're right and had been all along, and the support that they had given you was, was vindicated.
I couldn't have lived with myself if we had done no investigating ourselves. It was just something we both felt we needed to do. We didn't even discuss it. We just knew that's what we would do.
After United Flight 811, the locking system on the Boeing 747 cargo doors was changed. Inspections were increased. Another potential cause of explosive decompression had been found and eliminated.
That is an amazing accolade to what we've learned, not just Boeing, but what we've learned about maintenance, about structures, maintaining them, and inspecting them.
Since the first jet engines pushed planes higher in the sky, the aviation industry has struggled to harness and contain the deadly power of pressurized oxygen. They know all too well that a single flaw can lead to a terrifying decompression. But more than 15 years after United 811, another deadly lesson is learned.
Do you read? Over?
It's August the 14th, 2005. For almost an hour, Helios Flight 522 has been circling the skies over Athens.
Helios 522, over.
Its flight crew has stopped communicating with air traffic control. Fearing a terrorist attack, the Greek Air Force scrambles 2 fighter jets to circle the mystery aircraft.
One of them was actually in a shooting position behind the 737. The other one was nearby the cockpit, and he was trying to communicate visually with the person in the cockpit.
The fighter pilots can't see any damage to the jet. No holes in the fuselage.
There is no structural failure. There is no fire. There is no problem, obvious problem, from the external view with the plane.
Someone in the cockpit waves at the fighter pilot. But all too soon, the jet loses altitude and falls towards the ground. All 121 people on board are killed. It's the worst air crash in the history of Greece. Within minutes, investigators are on the scene.
So we climbed over the hill, and there we were, facing this situation, which was beyond any description. I saw a great area in front of me, which was burning. It was black. Burning, people spread, pieces of the airplane.
The autopsies add more mystery to the case. Everyone on board the Helios flight was alive up to the moment of the crash.
They did not die from inhaling a toxic substance in the airplane or from an explosion. These people died on impact.
But if the passengers were alive until impact, why didn't the fighter pilot see more activity on the plane? Akrivos Tsolakis is the lead investigator. He begins to dig through maintenance records. He learns that on the day of the crash, the rear door had been inspected for leaks. Before it took off on its last flight, the Helios jet arrived in Cyprus with a problem. During the trip, the cabin crew had heard loud banging and saw ice on a rear service door. To make sure there's nothing wrong with the seal on the door, the engineer runs a pressurization test. He's looking for a leak.
So explain again how you tested the pressure.
I went into the cockpit,
I turned the pressurization switch to manual.
Switching digital pressure control unit from auto to manual.
The jet's engines are turned off, so the engineer uses the plane's auxiliary power unit to force air into the cabin.
It's like looking for a leak in a tire. In this case, what you're having to do is pressurize the aircraft, use a barometer essentially to monitor the pressure inside, and look for leaks that way.
A normally well-maintained jetliner of any age is simply not going to be completely airtight. You're going to have leaks. As a matter of fact, as pilots, we know that certain airplanes are going to leak more than others, and you've really got to crank the pressurization up.
After completing the pressurization test, the ground engineer reports that the jet is in good working order. But the digital pressure control is left in the manual position.
They were supposed to return the selector to the auto position.
If the flight crew fails to see that the switch is on manual, their plane won't properly pressurize. The oxygen available inside the plane will be just as thin as the outside atmosphere. The passengers will be directly exposed to a deadly environment in which they cannot survive. August the 14th, 2005. The worst airline disaster in Greek history has stunned the nation. Investigators are sifting through the gruesome wreckage. A few minutes after 9 in the morning, Helios Flight 522 left from Cyprus bound for Athens. The crew has no idea that hours before takeoff during a maintenance test, a flight engineer has left a pressurization switch set to manual. Both the captain and co-pilot miss the fact that the plane is not set to pressurize automatically. As Helios 522 climbs, an alarm blares in the cockpit.
What is it? The takeoff config warning?
It's a non-pressurization warning, but it sounds identical to another alarm. The pilots confuse the two. It's a critical mistake.
The alarm sounded, and that alarm was misinterpreted. Most of flight crew, they will never face an alarm with no pressurization in all their flight career because it's a rare event.
Operations, this is Flight 522, over.
Flight 522, what can I do for you?
We have a takeoff config warning on.
Sorry, can you repeat?
As the pilots troubleshoot with ground engineers, life-sustaining oxygen is slowly seeping out of the plane. Eventually, oxygen masks drop in the cabin. They do not fall in the cockpit.
The reason that we don't have automatically deploying oxygen masks in a cockpit is simply too much up there, and if you had things popping out, they're going to hit switches that they shouldn't hit.
The crew don't realize they have a pressurization problem. Eventually, both the captain and the co-pilot collapse unconscious. The oxygen is too thin to breathe.
We're the ones that should be trained consistently to understand that ears popping, anything that indicates pressurization, you don't even talk to each other before you grab that mask and put it on.
The passengers are unaware that the plane is now flying itself. In emergency situations, chemical generators above the seats pump out oxygen. But there's a catch. These generators only produce enough oxygen for about 12 minutes.
Well, the problem with the passenger masks is, for one thing, they're not designed to keep you oxygenated at a high altitude. What they're designed to do is give you enough oxygen so that you can survive until the pilots get the airplane down to a low altitude.
But with both pilots already unconscious, the Helios jet did not descend so passengers could breathe without assistance. Instead, the plane flew on autopilot to Athens. When the oxygen supply stopped, the passengers passed out. By the time the Greek Air Force intercepted the Helios jet, only one person was still moving. Likely surviving with bottled oxygen, flight attendant Andreas Prodromou was still conscious when the fighters approached. He made it to the cockpit, but he couldn't save the plane.
Asinine Control, there is one person moving in the cockpit of Helios 522.
Eventually, when its fuel ran out, Helios 522 crashed. Investigators eventually find the panel with the pressurization switch.
Are you sure this is the way it was found? It hasn't been moved at all.
All 121 people on the Helios flight died because their plane didn't carry enough life-sustaining oxygen as it climbed into the sky. It's been more than 50 years since the beginning of the passenger jet era. 50 years in which the industry has learned, sometimes painfully, how to safely fly more than 10 kilometers in the sky.
When you look back at all the other accidents over the last 20 years, in most cases, we were pushing the frontier of knowledge.
Unfortunately, when you're pushing the envelope, you're pushing the boundaries of design, you can encounter problems that you hadn't anticipated.
In search of the safest plane imaginable, the history of aviation traces a flight path through tragic accidents to technological breakthroughs. Many of these accidents display the incredible power of explosive decompression. The Airbus A320 and every other passenger plane built today is infinitely safer than the first jets that flew in the 1950s. They have to remain safe and get even safer because we rely so heavily on this incredible mode of transportation that takes us somewhere we were never meant to be.